Hello, my name is Lizzie Kendon and I lead a team of people at the Met Office Hadley Centre using very high resolution models to try and understand future changes in climate and hazardous weather. So firstly, I'd just like to thank the people listed here on my slide who've contributed to this talk. Here I'm primarily focusing on regional models. So these are models that span a limited area of the globe and are driven at their edges by a global climate model. And the key advantage of that is they enable us to afford to run at much higher resolution in more detail than we can afford to run globally. And in my group, we're particularly interested in running at very high resolution, so we so-called convection permitting resolution. So that is where we have a mid-model grid box of about 1 kilometre or so across, compared to a more traditional climate model where you might have a grid box of tens of kilometres across. And that's important because it allows us to much better represent the small-scale behaviour in the real atmosphere, and in particular convection. So convection is a key process behind many of our local weather extremes. Also, when we have this much greater detail, we're able to better represent mountains, coastlines and cities. The figure here on the right-hand side is just illustrating how much better we can represent rainfall across the UK, for example, as we go down in model resolution from 300 kilometres all the way down to where we are now at about 5 kilometres or less. And you can see you can capture heavy rainfall over mountains and the rain shadow effects across the UK in much better detail. There are weaknesses in this approach, so you're driven at the edges by a global model, so how reliable the regional climate projections are very much depends on the quality of the global model, and also we're better representing these small processes in the atmosphere, but they're not really feeding back to the large-scale weather patterns, and that could be important in some regions. So what do we know? So these high-resolution convection permitting models provide credible projections of future changes in hourly precipitation extremes and other high impact phenomena. So what I'm meaning here is heavy summer downpours, hail, lightning, maybe wind extremes. And we're moving beyond kind of broad statements like hotter, drier summers, warmer, wetter winters to really providing detail on changes in local weather extremes over the coming decades. And what we're finding is that increases in extremes are larger in many cases than we previously thought. Now, as part of the UK Climate Projections Project, we recently released the first national climate scenarios at this convection permitting scale. So here I'm meaning a model that is as detailed as that typically used for weather forecasts, now used in climate change. And this is a really big step forward in national capability and is allowing us to try and understand changes in storms and downpours, severe wind gusts, but also to feed directly into impacts models to look at future changes in flash flooding, to look at changes in cities and urban extremes. So here we have 12 projections and they're using the high emissions scenario RCP 8.5, and we have data for periods going right out to the end of the century. Now these models give a much better representation of how our rain varies on a day-by-day and hour-by-hour basis, in particularly how intense it is, but also how long it lasts, and that's really important if we want to know how changes in flooding, for example, may materialise over the coming decades. For example, here you can see an example of an event in flooding, the Easter floods back in 1998, which is just chosen here to be illustrative of the much better realisation of rainfall in these models. You can see the detail on the frontal system there, and also the showers to the north and west, the much more detailed resolution you can see there. And also in the regional model on the right hand side, it's brown, a lot of brown colours, so light rainfall, and that's typically what we see in coarser resolution models. But for the first time, these models are really allowing us to provide credible information on changes on hourly scales, so sort of rainfall that's predominantly important for flash flooding. Now in UK CP18, we had the headline message that we expect a greater chance of warmer, wetter winters and hotter, drier summers in future across the UK. But this high resolution model is now showing us how, in addition to that, we can expect more frequent and intense extremes as well in future. Now, here are some examples of the results coming out from this model. It's important to say that this is for the RCP 8.5 scenario. That is the situation if we don't curb our emissions. But clearly, if we follow a lower emissions pathway, then some of these changes will be considerably less. So we find that hot summer days will warm by 3.7 to 6.8 degrees C. And in particular, within that, if we consider hot spells, so these are days exceeding 30 degrees C for 2 days or more. So this is what we typically use to issue a public health warning. They're 16 times more frequent over the southern UK by the 2070s. The model's also telling us new things about how rainfall might change. So although we get an overall summer drying, actually the intensity of rainfall within that may increase. Also, it's a surprising result perhaps to us was that we're finding a great increase in winter precipitation over the UK in this model. So a 26% increase in mean rainfall across the UK compared to a 16% increase. And we now understand why that is, and it's because how accurately we're representing convective showers which are triggered over the ocean in the warmer climate and then advected or moved inland. And that's a process that isn't well captured by coarser models. We're also able to now look at frequency of days with hourly rainfall exceeding 30 millimetres per hour, for example, which is a threshold typically used to issue a flash flood alert. And we find the frequency of those days almost doubles by the 2070s, again, if we follow this RCP 8.5 scenario. Now, we're also trying to provide information here about uncertainty in the future response, which is really important if we want to understand the likely range of changes in the future. And for the first time here, we have an ensemble, so that's multiple realizations of the climate at these very high resolutions. And so we can give some indication of uncertainties at local and hourly scales. But these models are only downscaling Hadley centre models. They're not downscaling the full set of global models. And the importance of that can be illustrated here in this figure, where we're looking at responses for summer temperature, summer precipitation, winter temperature, and winter precipitation across Scotland and England. The green is these new high-resolution 2.2 projections. Pink is the 12-kilometre model. The yellow is the Hadley Centre global models. And then in blue is the CMIP models. And these are all products as part of the UK CP18 suite. And what we can see that is in some of the Hadley Centre sets are primarily sampling warmer, drier outcomes, and the greater range observed in blue in the CMIP 5 set. So it's really important to see these UK CP18 2.2 projections in the context of the wider sampling of uncertainty from the other UK CP18 products. But they are also telling us something new. So on the bottom right here, you can see that some of the projections in green for the 2.2 kilometre model is outside of the probabilistic projections in black. So it's telling us that large increases in winter precipitation across the UK may be much more likely than we previously thought when we start to capture some of these detailed processes. So moving beyond the UK, we've actually run these high resolution simulations for Europe. This animation here is really illustrating the improved realism of rainfall, so you can see the better representation of the front and the trailing showers to the west, and also the daily cycle of rainfall is more realistic in this model. And what we find when we start to look at future changes across Europe now, we see again that increases in precipitation extremes are larger than we previously thought. So here we're looking at different percentiles of the distribution, so more extreme rainfall on the left-hand side, and you can see that in red the future changes are consistently larger for all these different regions of Europe in the high-resolution model, 2.2 in red, compared to the global model, 25-kilometre resolution in purple. And this result is quite consistently coming out in lots of these sort of studies for other parts of the world as well. So we're gaining new understanding of how climate will change locally using these models. Now, as the atmosphere warms, it can hold more moisture. In fact, we get 7% increase in moisture holding capacity per degree of warming. That's something we know very well and we see in coarser models. And that is expected to lead to a similar sort of increase in rainfall extremes. But what we're finding in these models is that it can go beyond that, so there can be an amplifying effect. And this is how we capture small-scale processes and storms, and that can amplify these increases to rates much higher than that. We're also finding evidence that storms may last longer across Europe. So this is really important because it obviously leads to high rainfall accumulations. So we're not just talking about high rainfall rates, but also lasting for longer. And some work done by Abdullah in my team has shown that if we look at how conditions associated with high rainfall rates, so lots of moisture and uplift, they're about 7.5 times more frequent in the future across Europe. But if in addition we look at when their systems are moving slowly, so they have the potential for high accumulation, so high flood potential, they're 11 times more frequent in the future across Europe, again using this RCP 8.5 scenario. We can also look at other phenomena, so here extreme wind and sting jets. So sting jets are kind of small scale features within a storm system, so they can kind of be thought of like a sting in the tail. They lead to very damaging winds. And these high resolution models now start to allow us to capture these features. You can see along the top some historical storms and a much better representation of the observed distribution of damaging winds in black in the region in the high resolution model in red compared to, say, for example, the reanalysis data in blue. And if we start to use these models to look at how damaging winds might change, we find that events exceeding 40 millimeters a second are 3 times more frequent in the future, with almost half of this increase coming from sting jet storms. So these are these local phenomena, only captured really in these high resolution models. Now, if we look at another part of the globe, Africa, again, we're learning about how not only wet extremes might increase more, but also dry extremes too. So what we found is that if we consider a threshold, for example, 60 millimeters in 3 hours, which can lead to the sort of flooding you can see in those figures on the bottom there, that's 7 to 8 times more frequent in the future over parts of Africa. But it also, if we start to look at how dry spells may feature, particularly in the wet season when farmers are growing crops, we find these are almost 2 times more frequent in the future compared to the present day. These are changes that weren't seen in the coarser model, and it's down to how these high resolution models are capturing changes in the stability of the atmosphere, if you like, as we're warming. Again, it's important to say that these changes are for the RCP 8.5 scenario, and if we do curb our emissions, then the changes and the impact will be less. What are the key knowledge gaps? So it's really important for us to try and understand which climate signals can be reliably captured by more traditional climate models and when we need high resolution, and there's still lack of knowledge in some cases there. We also find that heavy rainfall tends to be too intense. What does that mean about how reliable our projections are from these models? What about other high impact phenomena at local scales? And also there's limited sampling of uncertainty for changes in extremes at these local and hourly scales. So let me talk through some of these points. So back in 2017, published a paper in BAMS identifying which type of features, for example, we might need these high resolution. We identified summer rainfall intensity and duration, severe wind gusts, short duration rainfall extremes, and potentially also fog, lightning and hail as all being phenomena for which we need high resolution models. But since then, we've gained some more understanding, and that's the boxes in purple. So we've learnt now that not only for those things, but also wintertime convective showers, high resolution models can tell us something new, which in turn can actually feed back into large scale mean rainfall changes. And also we need high resolution with better representation of tropical cyclones. Also in some parts droughts and summer heat waves because of the better representation of the local processes, and also the kind of soil moisture and how that might feed back on these changes, which is important. Now, in these models, what we tend to find is heavy rainfall is too intense. And this is because the model, although high resolution, has a grid box of the order of 1 kilometre or so across. Really, convection happens at a much higher resolution than that, so the order of 100 metres or so. So we're not fully resolving convection, and that leads to heavy rain, the updrafts being too deep, and therefore we have too much heavy rainfall. And that's likely to be also true in our future projections. But does that mean the changes themselves are correct, or incorrect? Not necessarily. And I think an important piece of evidence is shown here. So these are return levels of rainfall, so extremes of rainfall for 2 years out to 30-year return levels. And what you can see in black is the observed, and then red is the different realisations from UKCP, and you can see they're all shifted upwards, so they're all a bit too heavy rainfall, but the shape of the line is captured well, whereas that's not the case for the blue, which is the coarser resolution 12 kilometre regional model. You can see that the lines here are too steep. So what this is telling us is the rate at which extremes increase as conditions become more favourable, so as they become rarer, is well captured. And we hope that will extend into the future, which will give us confidence in the future change projection. But I should say there's quite a lot of work going on to develop scale-aware convection schemes, as they're termed, to improve schemes that will help us to address some of these biases in these models. Due to the fact that we only have a small number of realisations, because these climate change models are very expensive, we have a really limited sampling of uncertainty. As I said, in UKCP we have this first ensemble of 12 members, but also there's other work going on to complement that as part of the Cordex, FPS and EUCP projects, where we're starting to provide an indication of to what extent these results are really robust across different models. And indeed what we find is this tendency for heavy rainfall to be higher in these high resolution models compared to more traditional models is a consistent result across all of these. So you can see here in all these different parts of Europe and these different models, we can see that the red is higher than the blue, so this greater intensification. It seems to be a consistent, robust result. What are the opportunities for progress? Improved representation of complex land surface processes. I'll talk about that more in a minute. Inclusion of ocean coupling and earth system processes. We're now starting to be able to run quite a few of these experiments, multiple realisations, and a key opportunity for progress I see is synthesising all this information, both from these models and other modelling systems, to give an improved understanding of future risk. We're also moving towards global convection permitting models. So correctly modelling what happens to rainfall at the land surface is a key challenge, and perhaps even more so in these really high resolution models where rainfall is so much more realistic and intense and intermittent, and so less able to infiltrate the soils and tends to run off too much. But as we start to build more complex ground soil water schemes, so for example the top model as I'm showing here, this can lead to real improvements in how we represent soil moisture with less rainfall running off at the surface. Also, we're starting now to be able to link ocean and wave components to the atmosphere, and this is part of the UK Environmental Prediction Initiative. And this is important because it allows us to look at combined hazards at the coast, so where we have both storm surges and river flooding and heavy rainfall all at once, and how that combines to give flooding at the coast. Also including more earth system processes increasingly, so biogeophysics, biogeochemistry and vegetation dynamics. Now, in this figure here, I'm trying to show how we're developing our modelling systems through to user application and where there are real opportunities for making progress. So if we start in the pink box, the current state of the art, if you like, is a single large simulation at these kilometre scales over Africa. But now we're moving through to having many of these realisations, so ensembles, both for Africa but other parts of the world, so Europe and the UK for the UK CP18 projections. And we want to try and synthesise this new information, these new ensemble information with the latest multi-model information from the global models to provide a much better understanding of present day and future risk. And I think this is a really area for work moving forward, how we combine all this information to give a much more higher quality predictions for user application. But in parallel to that, we're also developing the modelling systems themselves. And I very much see the next generation for regional modelling to be these kilometre grid scale models, but also with much better representation of land surface processes, larger domains, and coupled to the ocean. So finally, what can users expect over the next few years? So in the next 2 years, part of the UK TP project, we'll be delivering projections sampling a much wider range of uncertainties, so now downscaling different global models. So that's important as it will allow us to give a better estimate of uncertainties in changes in local weather extremes. Also research looking at changes in other high impact phenomena, hail and lightning, and a better understanding of changes at small scales over cities. This figure on the right here just illustrates how much better the urban heat island, for example, is represented in these high resolution models compared to a more traditional regional climate model. Also, we are running climate simulations now continuously at these scales, so allowing us to look at the evolution over climate through the coming decades out to 2100. So not just climate now and the climate at the end of the century, but how it's going to evolve through time between those periods. In the next 5 to 10 years, I see us having updated projections with improved representation of the soils, and that's really important for getting better projections of runoff, but it's also especially important in inland continental regions like, for example, over Central Europe, where these processes can be particularly important. Also, we're developing these new convection schemes, which will hope to reduce some of the biases we still have in these models, but also give us the opportunity for more consistent global and regional projection systems. We're also starting to introduce coupling, as I said, with the ocean, which is important for combined coastal hazards and understanding changes in those. Increasingly, we're going to be able to afford ensemble simulations, so multiple simulations at these scales, which will allow us to understand uncertainty and changes in other parts of the world, so Europe and Africa. And also we're moving to these larger domain simulations so we can capture how remote influences, so things that affect us further away, and how and capture those at much higher resolution, which can be important for our local projections. So with that, I'll stop there and just list the pledges that I have personally to reduce my carbon. Thank you.